Hi class, welcome to the last and final lesson in Unit 4, the periodic table. In this lesson, we will describe the trend for ionization energy across a period and down a group and explain why these trends exist. We will also describe the trend for electronegativity across the period and down the group and explain why these trends exist. Ionization energy, abbreviated capital E, is officially defined as the energy required to remove the most loosely bound electron in the valence shell. It is found on reference table S. It is very important that you become very familiar with the definition of ionization energy and then later on also the definition of electronegativity. Because when the Regents wants to ask you which element has the greatest or least ionization energy, they don't ask you flat out. Instead, they're going to ask you which element requires the greatest amount of energy to remove the most loosely bound electron in the valence shell. And then so we know that we're referring to ionization energy. Now, we have to know the trends for ionization energy across the period and down the group. Let's start with across the period. Here we have a snippet of our periodic table, and we're looking at period number 3. Period number 3 begins with sodium and ends with argon. But when we look at the ionization energies, what you can see is generally the ionization energies are increasing. Now, there are a few hiccups along the way, like when the ionization energy of magnesium is compared to aluminum, but we're not going to focus on one or two hiccups, but instead we're going to focus on the overall trend. And so as we can see from reference table S, as we go across the period, our first ionization energy increases. Now, why does ionization energy increase across the period? Because as we move across the period, we add one more proton to each nucleus. This creates a stronger nuclear pool, which makes it more difficult to remove electrons. So when we compare aluminum, which has 3 principal energy levels of electrons, to chlorine, which also has 3 principal energies levels of electrons, we can see that chlorine's more positive nucleus is going to pull on the electrons more tightly, making them more difficult to lose. So the weaker the nuclear pull, the lower the ionization energy, and the stronger the nuclear pull, the higher the ionization energy. We also need to be familiar with the trends for ionization energy as we go down the group. Now, going down the group is a little bit more tricky because the atomic numbers don't simply increase in a series by one, but instead they're a bit scattered. But as we examine the ionization energy for elements in group number 1, generally we can see that the ionization energy is decreasing. Why does ionization energy decrease as we move down the group? Because as we have larger atomic radius due to more principal energy levels, there is less nuclear pull on those outer electrons, meaning it's easier to take them out. So as we go down the group and we add a ring of electrons known as a principal energy level, we decrease our nuclear pull, making our ionization energy lower. So by now, you should be able to describe the trend of ionization energy across the period and down the group and explain why these trends exist. The other periodic property we're going to look at is electronegativity. Electronegativity is defined as the attraction for electrons Some atoms like to attract electrons in a chemical bond so they can obtain a more stable, lower potential energy, noble gas valence electron configuration. Electronegativity is found on reference table S. Electronegativity sounds very different from first ionization energy, but you'll see that its trend is still very similar. Electronegativity is a scale ranging from 0 to 4. The highest number, 4.0, represents the most electronegative atom. That is fluorine. So fluorine has the strongest attraction for electrons in a chemical bond. So fluorine has the strongest attraction for electrons, as it is only one electron away from gaining a stable, noble gas valence electron configuration. The closer any atom is to fluorine, the higher its electronegativity will be. Now, what's the trend for electronegativity as we go across the period? Let's look here at period number 3. When we examine the electronegativities on reference table S from sodium to chlorine on period number 3, you can see that electronegativity increases as we move across the period. Again, don't memorize the trend, just know how to look it up on table S. Why does electronegativity increase across the period? Because as you have greater nuclear pool, the nucleus has a greater chance of attracting an electron. So as we go across the period, all the elements in period number 3 have 3 principal energy levels or rings of electrons. But as the nucleus gets stronger, it'll be better able to attract electrons. So aluminum has a weaker nucleus, so it is a weaker attraction for electrons. And chlorine has a stronger, more positive nucleus, so it will have a greater attraction for electrons. We also must know the trend for electronegativity as we go down the group. Again, the atomic numbers down a group are not serial, but instead we'll have to look them up. But when we look up electronegativity for these elements in group number 1, you can see as we go down the group, electronegativity is decreasing. Why does electronegativity decrease down the group? Because as we increase the atomic radius when we add a ring or principal energy level of electrons, we will have less nuclear pull. So that means we'll have a lower attraction for electrons in the valence shell. As you move down the group and you add a ring or principal energy level of electrons, you're going to have a weaker pull for electrons or a weaker attraction for electrons. So by now, you should be able to describe the trend of electronegativity across the period and down the group and explain why these trends exist. Here is a nice summary table that explains the trends we've looked at thus far this year. We looked at metallic character in unit number 1, and we're revisiting it here in our periodic table unit. Recall that metals tend to be to the left on the periodic table, to the left of the bold staircase, and nonmetals tend to be towards the right of that bold colored staircase. In this unit, we've examined atomic radius, ionization energy, and electronegativity. These values are all found on reference table S, so you don't need to memorize their trend. Just make sure you know how to look them up on reference table S. This concludes lesson number 28, the last and final lesson in the periodic table unit. Make sure that you've taken good notes. Write down any questions you have, bring them to class, and ask them. Complete your homework on Google Classroom, and put your Regents Chemistry reference table and calculator back in your backpack so you are prepared for class. I'll see you soon.